Thank you, Fernando, and thank you all guys for staying until the very end. I know it's a bit late and we all want to go and see the war series. Okay, so I'm going to talk to you about some work that so this project is ongoing, and this is in collaboration with Raíssa Mendes from Universidad Federal de Brasil in Rio de Janeiro, and Jan Steinhoff from Albert Einstein Institute in Germany. So this is the take-home message. What we do, what I'm going to talk about, is the exploration of the possibility to constrain massless scalar tensor theories of gravity using the oscillation spectrum of neutron stars in gravitational waveforms. So if you want to go home now, just take the message, and I won't be offended. It will be fine. If you want to stay, then I'm going to make a very brief introduction to scalar tensor theories. I'm going to tell you how do we compute the oscillation spectrum, and how do we want to probe the theory or constrain the parameters of the theory using such oscillation spectrum. So this is my plan. I divided my talk into 4 parts. In the first part, in 10 minutes, I intend to do a very quick, very basic introduction to scalar tensor gravity.
Now? Is that working now? Okay. So that means that you guys missed 5 minutes of what I said, I guess. Could you hear what I said? Okay. Or should I start from the beginning? Is it okay?
I can hear it.
Okay. Yeah, I was saying that I will divide my talk into these 4 parts. The first, I will do this very brief introduction to scalar tensor gravity. Then I will tell you what this spontaneous scalarization business is about. And then I will tell you how to compute the radial oscillations of scalarized neutron stars. And in the end, the potentially most exciting part of this talk is precisely what is work ongoing, so we just have preliminary results. I will present something that might not be publishable as it is, but this is exciting and I want to share it. And then I will do a very brief summary, apparently in no time. Okay, so massless scalar tensor theories of gravity. Those are among the simplest possible ways to extend general relativity that you can imagine. It's just adding an extra degree of freedom that is not a tensor, it's not a vector, it's just a scalar field. Yeah, the interpretation of the field itself can come from different fronts, right? If you are a cosmologist, you would think of it as a field describing the dark sector of the universe, or if you come more from the theory side and you are a string theorist, and you take the low energy limit of string theory and compactify dimensions, etc., you end up with an effective field theory that looks pretty much like a scalar tensor theory, and you would interpret the scalar field as a dilaton. So that's another way of interpreting it. Yeah, so in particular, what I will be focusing on is this kind of action here, where we have a kinematic term here. I'm not introducing any potential, so because I want to keep as simple as possible, as I said in the beginning. If you notice, there is no coupling to the Einstein-Hilbert action here of the scalar field. There is no explicit coupling there, but the coupling of the scalar field phi is through the matter action. This Sn denotes an action for a collection of matter fields denoted all, collectively in this psi, this big psi. This could be fluids, electromagnetic fields, whatever you can imagine. And yeah, so what people do is, well, they call this A, the coupling function, and it is assumed that the cosmological evolution, of course, of the universe would set a constant background value for the scalar field at the present time. So if you call this present time tau naught, then this phi naught is what is going to represent the value of the scalar field that permeates the whole universe. A convenient definition that might be useful in the following slides is this log derivative of the coupling function. And here there is an abuse of notation in the literature. Some people call this alpha to be the coupling function. I will be referring to alpha and A as the coupling function, interchangeably. It doesn't really matter. So what is usually done also is this Taylor expansion around the cosmological value of the scalar field, and then you are interested in situations where you have a compact object, say a neutron star or something, that modifies the space-time in its vicinity, but then as you move away, then you recover the scalar field, the cosmological value of the scalar field. So that's why it makes sense to expand around the cosmological value and look at situations where you modify this. I feel like I'm missing some important comment here. Okay, I will remember later. By the way, these are the field equations. When you vary this action with respect to the metric or with respect to the scalar field, and with respect to the scalar field, you get these field equations where you see the coupling function appearing in the right-hand side of the equations. And you see this T without indices. This is a trace of the energy momentum tensor. And you see that the scalar field obeys a wave-like equation with a source. The source, of course, it's in terms of the trace of T mu. I remember now what the comment is, the thing that I was forgetting. No, I forgot it again. Sorry. What was this about? Huh? No, but I just remembered. I'm writing this action in a particular frame that is called the Einstein frame. Yeah, that's an important thing to point out. In this particular frame is where you have no explicit coupling of the field to the geometry sector, right? You could do a conformal transformation and go to a different frame, which is called the Jordan frame, where you would have an explicit coupling of the matter fields, of the scalar field to the geometry. This is more convenient because here the field equations have a simpler form, but the other field is computationally more convenient because things simplify a little bit. So, okay. That was my very brief introduction to scalar tensor theories. Now, let me talk about this non-perturbative phenomenon that occurs in neutron stars in the context of scalar tensor gravity. It turns out that in the expansion that I presented in the previous slide, here you keep up to the linear term, you keep beta not different from 0, then you end up with a theory that is called after Damour, Esposito, and Farese from the 90s. These people found that when they constructed neutron star models within this theory, and you choose sufficiently negative beta naught, then the theory predicts this non-perturbative effect in compact stars known as spontaneous scalarization. So I'm going to tell you in a moment what that is more precisely. But let me say that when I say compact stars, what I mean is models of compact solution. Models of the stars thought as solutions of the Tolman-Oppenheimer-Volkoff equations. So those are solutions to the Einstein equations, where you have a spherically symmetric source of matter, which is actually a fluid. It's usually a perfect fluid, and your favorite equation of state. So you plug that matter source into your field equations, which I already wrote there for you. You solve that, usually numerically, because as far as I know, there are no exact solutions within scalar tensor gravity. And then you construct models for compact stars. Then a very common way of parametrizing these solutions, these TOV solutions, is in terms of the compactness ratio of the stars. So this is a total mass of the star, and this is its radius. So every point in the x-axis is a different star, and here you would consider the total baryonic mass of the star. So you would get a sequence of solutions. As I say, each point in the curve represents a star, where you see a one-to-one relation for any given compactness for a star. You get only one baryonic mass, and then there is this critical point, which is the turning point of the curve, where this is a very special critical compactness ratio. Let me call it C, just for critical. To the right of that, you have unstable GR stars. I don't want to call them GR stars, because we are in the context of scalar tensor gravity, but what I mean is phi equals 0, so these stars have no scalar field, but effectively that is the same as general relativity solutions. So what happens in the scalar tensor gravity is that there is a critical compactness, let me call it a point A, where a different branch of TOV solutions detaches from the GR branch, and it does something like that. So each point in the line represents a different star, but with a non-trivial scalar field profile, a spherical halo of a scalar field surrounding the star, peaking taking a maximum in the center of the star and then diluting as you move away from the star. There is another certain compactness where the branches join again, and then you have the general relativity solution again with no scalar field. So this is called the scalarized branch of solutions, and now the one-to-one relation is broken, because for one given compactness that you choose, you have two possible baryonic masses, so you have two possible configurations. Each star in that branch is actually described in terms of what is called a scalar charge, Q, which is defined in terms of the asymptotic behavior of the field. When R goes to infinity, you have the phi naught, which is the cosmological value, plus what is called the scalar charge over R plus lower order terms. So this Q is what characterizes each scalarized star, and it does something like that. It is 0 here, of course, because in general relativity, or when phi is 0, there is no scalar charge. Okay. Yes.
Shouldn't it be 0 in the crossing point? Maybe you are crossing that line at once.
The crossing point, which crossing point?
Between A and B.
A and B, the scalar charge is non-zero.
Between A and B, you are crossing the GR line once.
Yes. And there? No, not necessarily. Yeah. Scalar charge is probably even maximum there. I'm not sure, but it does.
One crossing point, or can you have multiple?
You can even have multiple, yeah. But within this, the Moore-Esposito-Fales theory is generically only one. Yeah. Okay, having said that, yes?
But there's not some consequences on this limit on the compactness of star. I don't remember well, but there's a theory, right, that goes that theory that the GM over R has to be less than 4, if I remember well.
No, this is above that limit. That what you're talking about is, I don't remember the name of the thing, but it's a lower bound for the possible compactness of a star, which is 9/4 the compactness or something.
You have some
This is safe, this is away from that, yeah, yeah. And because that is for uniform density stars. So this is non-uniform profiles. I'm sorry? Okay, yeah, yeah. Okay, one last thing that I forgot to mention is there's another maximum here, analog to that one, where if you move to the right of there, you again have unstable, or you expect to have unstable scalar tensor solutions. Let me write here GR stars, and stars as well here, just to be consistent. And where I say unstable is against gravitational collapse. What I mean is that if you perturb one of these solutions, they would collapse and form a black hole. And you expect the same for configurations here. Although this is not obvious. You have to check that. I'm going to tell you in a moment how we check that. Okay, where is my pointer? Okay, there's a very nice work from the 90s, 93 I think, by Harada, where he does this linear stability analysis considering small perturbations around the cosmological value of the field, and then he plugs that into the field equations and the matter equations, and it turns out that the perturbation of the field, the dynamics is described by this wave equation with a source, again, the source being in terms of the parameter beta of the theory and the trace of the energy momentum tensor. And for T negative and beta not negative, there are unstable modes. That is because the overall sign of this effective mass here is minus, is negative. Then you have solutions that grow up. For arbitrary small times, the amplitude just grows up. That is what is usually referred to as a tachyonic instability, because modes would propagate faster than the speed of light, and then it turns out that the onset of the stability just coincides with the domain between A and B. So this instability triggers spontaneous scalarization. That is why this work is interesting, and there will be a connection between this instability and something that we do in a moment. As I was saying, the end state of this instability under phi perturbations, or scalar field perturbations, are precisely scalarized solutions. This is something that was numerically checked independently for neutron stars in scalar tensor gravity by Novak in '98, and then Miguel Alcubierre and Milton Ruiz and other people, I think Darío was in that paper as well, they were doing something similar, but where the matter fields are not fluid. I mean, those are not neutron stars because they are not fluid stars, but they are bosonic fields. There you have a bosonic field, and on top of that you would have the scalar field related to the scalar tensor theory. What they do schematically is they take one star that is there, they do the perturbation numerically, and they see the transit towards a scalarized solution. So, as we know, those are unstable by the work by Harada, and these would be energetically preferred, so the solution would transit dynamically to the scalarized branch. So that's pretty cool. Let me talk now about radial oscillations of scalarized neutron stars. As this implies, I will be focusing on stars that lie in the yellow line in the scalarized branch. And I'm going to consider scalar field and metric and fluid perturbations of that and compute the spectrum of oscillation of those configurations. The idea is to use the spectrum of pulsating stars to constrain the parameters of alternative theories of gravity. Notice that I'm not saying in particular only scalar tensor theories, but any theory that would have an extra degree of freedom, could be tensorial, could be true scalar fields, whatever. You expect to constrain the parameters of the theory based on, using the spectrum. I will show you in a moment more precisely what I mean. The disadvantage or the withdraw, if you want, is that fluid spectrum shifts induced by alternative theories of gravity, they are often small and degenerate with our ignorance of the equation of state. What it means is that the oscillation spectrum of scalarized stars are very close to the GRS spectrum, so it is difficult to tell if the little shift it can be mimicked just by changing the equation of state parameters. That's what I mean by that. So what do? We don't know. We look to somewhere else. And then, however, there should exist quasi-normal modes that are related to the additional degrees of freedom. And that is what we are after here. So, as I said, the idea is to consider radial perturbations of the metric and the star. So I'm working in a gauge where the line element of the metric describing, in the presence of the matter is described by this spherically symmetric line element where the metric functions are going to be perturbed, and also the scalar field, and also the fluid quantities. Turns out that the metric, sorry, I didn't write it here, but when the metric has a tilde, this is a metric in the Jordan frame. Remember that there are two frames where I can write the theory. And I mentioned that the Jordan frame is more convenient for calculations, so I compute the metric in this Jordan frame in terms of the perturbation in the Jordan frame as well, which is in terms of the perturbation of the metric in the Einstein frame, and also in terms of the coupling function. Whenever you see a note between parentheses, that means these are background quantities. So we consider Lagrange displacement to describe the fluid perturbations, which has only a non-zero radial component because we are interested for simplicity only in radial perturbations. And yeah, that induces fluid perturbations in all the fluid quantities, right? In the force velocity, in the pressure, the energy density, the baryonic density, and so on. So after lengthy calculations, one obtains ordinary differential equations that govern the dynamics of the perturbations. In particular, this is an equation for the scalar field perturbation, delta phi, and this is an equation for the Lagrange displacement. They are called master equations in the sense that when you solve for those equations are in generally coupled, but you solve the coupled system, and then you can reconstruct every other perturbed quantity. In particular, you can reconstruct the perturbation of the fluid quantities and the metric, etc. So in that sense, they are called master equations. They look nasty, and actually they are a little bit. Also, the good news is that they are linear. Of course, we are in the linear regime of perturbations, and they are ordinary differential equations. Yeah, and whenever you see these coefficients A, those are just background coefficients. But the problem is that those background coefficients are given numerically because, as I said before, these solutions that I was drawing here, they are numerical. So you have numerical information here, and you also have to apply your numerical methods to solve such a convoluted thing here. So how do we solve that? We solve the full master equations for radial oscillations, but I make emphasis that we do it without assuming the Coning approximation. If you guys are not familiar with the Coning approximation, this is something that is very commonly done in general relativity when you want to compute perturbations of a given background with the presence of matter. You usually keep the metric fixed, and you only study fluid perturbations. That is what is commonly known as the Coning approximation. In scalar terms of gravity, there is this dichotomy because how how do you decide if you keep the metric fixed and you allow for perturbations of the scalar field, or you fix the scalar field as well and you do allow for fluid perturbations only? So people have tried that in the past, like 20 years ago, and we decided to do the full thing without any coding approximation, and it turns out that that is a key point for the results. If you assume the coding approximation, then you miss the important thing that I'm going to show you in the next slide. So how do we solve those master equations for the perturbations? We follow two independent approaches and we check for agreement between those. One is in the frequency domain, it's a frequency domain approach where we take the following ansatz set, one for the Lagrange displacement, one for the scalar field perturbation, and we plug that into the master equations, and you have to manipulate them a bit until they take the form of an eigenvalue problem. Of course, you have to impose the right boundary conditions. You ask for regularity everywhere and outgoing boundary condition in the asymptotic region. In practice, it's not that trivial to do. So we wanted to check the solutions we obtained this way with the solutions we obtained with a more brute force approach, which is a time domain solution, where we consider the star in the center of our computational domain being surrounded by an initial, imagine this is a neutron star, and this is surrounded by a Gaussian shell that is initially at rest. Then you let it go. Of course, we're split into two smaller parts, one outgoing, one ingoing, but the ingoing part is going to come to the neutron star, it's going to hit it. You can think that as hitting the star with a hammer or something, and then the perturbation is going to go through the star, the perturbation is going to go away, and then the star is going to get excited, its natural oscillation modes. It will keep ringing with a relatively big amplitude, and then the amplitude is going to decay. If you picked a stable solution, then it's going to recover the initial, it's going to go back to the initial state. But then you put certain observers outside of the star to monitor the scalar field oscillations of that. Then you obtain a time series. Your observer would detect something like that. If this is delta phi, the perturbation of the scalar field. So this is time series of the perturbation. If you put your observer here, if you want, our observer somewhere here. It's a sphere actually. I'm drawing in spherical symmetry. This is for our observer fixed. And then you do a Fourier analysis of that in order to extract the oscillations, the frequencies of oscillation. There's a whole spectrum of that. And then you compare with the solutions that you obtain. Yes?
The non-perturbed solution corresponds to a scalarized star?
Yes, exactly.
Okay, so it's scalarized and then you perturb on top.
Exactly, so that you can do it without a scalarized star, and also makes sense. These equations do not require the scalar field to be non-zero necessarily. Even if you don't have a non-trivial scalar field, the delta phi is still there. Yeah. But what we do in practice is what you just said. Okay. Then, before showing you the results here, I wanted to sketch the results in the blackboard because I think it's easier to explain and easier to understand. So, you have to keep in mind my first drawing. And now, what I want to do is plot the frequency against the compactness ratio. The frequency is defined actually as the real part of this omega, of that omega, over 2 pi, I think. Then, in yellow, I would draw the GR picture. So around 4 kilohertz, you would have something that goes like this. The real part goes to 0, at the critical point C, then it keeps being 0, and the imaginary part becomes negative. That is related to the fact that C is a critical point where you have unstable stars that undergo gravitational collapse. This is what is represented by this. This is a fundamental fluid mode. Remember, yellow is for zero scalar field, which is equivalent to GR. Around 7 kilohertz, the first overtone looks something like that. If you want, I can write, this is the fundamental fluid mode. This is the first excited fluid mode. And then there is something that is associated to the scalar field itself, around 1 kilohertz. This is a critical point A and B. The real part of the frequency becomes 0 here, and then it's non-zero again, something like that. Right. So this is associated to the scalar field. So these are phi modes. The fact that it goes to 0 and the fact that the imaginary part becomes negative is associated with the tachyonic instability that I mentioned before, and with the fact that between A and B, we have the GR-like solutions are unstable against perturbations of the scalar field. So that is what is represented by this frequency going to 0 here, and by the imaginary part negative that I'm not drawing here. Now, in red, I'm going to draw a picture when we have a non-zero scalar field. For that, let me just mark these critical points here. So what happens is that the fluid modes are a little bit shifted like that. So each point in the red curve corresponds to a scalarized star, right? So this is what in the beginning of my talk I said that this small shift would be easy to confuse with a different choice of equation of state. But what has no analog in general relativity is the appearance of this part of the spectrum. It has no general analog because it is completely associated to the phi mode. This doesn't have anything to do with the fluid modes. So this is a new thing, and this is what you would miss if you don't work out the full master equations. If you assume the coding approximation, then nothing of this appears in your comes out from your calculations. So that is the relevant thing about this. And also something remarkable here is the size of the how do I call it, the magnitude of the frequency, if you want. It's lower than 1 kilohertz in general. So that is good news because that is closer at least to the sweet point of the sensitivity of the current generation gravitational wave detectors. So I'm not saying that this would be directly seen by gravitational wave interferometers, but this is closer, and that is encouraging, or we are optimistic about this. Something that I'm missing here is this other critical point that I mentioned, where unstable scalar tensor theories would appear here. This I would call C bar, and this would be represented here. By this frequency going to 0 at this C bar. And the imaginary part would go negative. Actually, I have a drawing of the imaginary part there. So what you see in the left is what I just drew here. And if you see blue and red lines, that is because we consider two different scalar tensor theories, but you can ignore one of those if you want. But in the right, you see the imaginary part of the frequency and the real part. This is zooming in into this region, well, this would be the critical point A, and this would be the critical point B, and this would be C bar, where the imaginary part will go negative, and that would correspond to this instability here. So what this is telling us is that it's the phi mode that determines instability of scalarized stars against gravitational collapse. So understanding that, I think it's pretty cool. Okay, as I mentioned, you could, when you consider perturbations of the neutron stars in this way, in the time domain approach, you can do a spectral analysis, and you can determine the whole tower of overtones involved in your oscillation. So, in particular, you might wonder how would it sound, because you know these frequencies here lie in the range for the audible bands of the human ear. So you could have fun just translating that into audible sound using Mathematica. It's not that difficult. And then how would a scalarized star sound if you hit it with a hammer? And how would it sound if it is not scalarized, if it's just a GR star? You can actually hear the difference. That's how it sounds, a scalarized star perturbed. And this is how it sounds when you only consider, when this is not scalarized and these are just the GR fluid modes. The reason why the pitch that you hear is higher in one, let me check which is higher. Which pitch is higher? It's the second one. And the reason is that in the second one, I mean, I'm picking, just for the sake of my gain, I'm picking one particular compactness ratio, and I'm making the sound with this frequency, with this, and with this for the first little bell. And for the second bell, I only take this, and of course the whole other tower. That's why the second sounds a bit higher pitch, because this lower frequency is not involved. Okay, but that doesn't really add much. This is just for fun. Okay, let me tell you. I think I still have time. 5 minutes? That's perfect. About phi-mode excitation in binary neutron star systems. So this is an interesting question. How likely are phi modes to get excited in astrophysical scenarios? Can they be probed using gravitational waves? So we want to explore the answer of those questions. Some potential scenarios are the following. It could be magnetar quasi-periodic oscillations. You know, magnetars are the most accepted explanation for these giant flares in the universe that only 2 or 3 have been observed recently, I mean, in history, and people have trouble explaining that, so one candidate explanation are magnetars. So this big burst would excite all the possible modes of a compact object, in particular phi modes, and if that leaves an imprint in the electromagnetic transient, then that would be something that we could use to prove these theories. Another possibility is to look at the spiral phase of in binary neutron star systems, and that's what I'm focusing on here. The third that I wrote here is the post-merger phase of binary neutron stars, where you could, in certain scenario, form a hypermassive neutron star after the two colliding objects merge. And there is this metastable state, which is called hypermassive neutron star, where all the possible modes would be excited. And if we can detect those with gravitational wave detectors, that would be great in order to distinguish between theories. And then gravitational collapse here, and I'm thinking on supernova core collapse in the context of scalar tensor gravity. You have a massive star that undergoes supernova, and then you look at the excitation of phi modes in the core. That would be another scenario. So let me just tell you about this ongoing project that I have with my collaborators. We are looking at the orbital dynamics of a binary neutron star system in scalar tensor theory, which can be obtained from an effective field theory. This is something that has been done, and it goes back to the pioneering work by Thibaut Damour and other collaborators, like in the past 2 decades, where they are able to write down an action from which they can derive the dynamical equations that describe the dynamics of a binary system that is made of 2 point particles. They started with 2 black holes, and they have been refining their models such that they can integrate out the microphysics related to neutron stars, and then they capture these microphysics, namely tidal deformabilities of a neutron star or oscillation frequencies of a neutron star. They capture those in coefficients of the dynamical system describing the orbital dynamics. So this would take me another hour to explain, and I'm not an expert on this. We are just using those results, those ways of writing down an effective field action from which you derive then you do a Legendre transformation in order to end up with Hamiltonian for the orbit that looks like this. By the way, I'm using here units where the speed of light is 1. That's why the units might look a little bit weird here. So labels A and B correspond to the 2 components of the binary, star A and star B. Each one has its corresponding mass, MA and MB. Each one has its corresponding momentum. So canonical pairs of variables are M and M and P in boldface P. And there's another pair of canonical variables involved here, which are Q, the scalar charge that I draw here in the beginning, and its linear momentum, because the scalar charge is also a dynamical variable involved in our dynamics. So Hamilton, you do the usual Hamilton trick to get the equations of motion, and it looks also something a bit nasty. There are many equations that involve radiation reaction forces, or if you want, radiative forces. These are the ones that model the draining of energy through gravitational waves, and those have been worked out by Thibaut Damour, like, I don't know, 15 years ago. They look something like that. There is quadrupolar radiation, dipolar radiation, and monopolar radiation due to the presence of the scalar field. The advantage of solving the orbital dynamics using these is that, of course, this is an ordinary differential equation system, and this is orders of magnitude less expensive to solve than a full numerical relativity simulation that takes months. So this runs in 5 seconds in Mathematica. You just set up a set of initial conditions, the initial positions and velocities of your point particles, and you let them evolve. You can give some eccentricity for your initial orbit, and you let it go. That's what we do. And in my last minute, I can show you the dynamic, how does it evolve the radial separation between the 2 points, the 2 point particles R, and these red dots correspond to the average of this radial separation per cycle. And I have to apologize about the units here. They are not very human readable because of technical reasons. I don't know. As I said, this is not meant to be published in the short time scale. So for some reason, we have it in that geometric units. And this horizontal line here signals the dynamical scalarization region. There's a whole story. This is not a spontaneous scalarization, but a different phenomenon called dynamical scalarization that is only associated to a binary system. This was discovered by Luis Lehner and collaborators, Steve Liebling, and somebody else that I forget, doing full numerical relativity simulations using this theory, they find that below certain separation, the stars scalarize dynamically. And we can recover that using our effective field theory. And it turns out that when the average of this radial distance goes beyond, goes beyond that threshold here, then the scalar charge evolution, which is drawn here, this happens around this 15,000 in this weird time unit. Then the scalar charge starts growing. This is an exponential growth, actually. And then if it has enough time, then it saturates. This is another situation where we have the radial separation, and it just has more time because we reduce the eccentricity of the orbit, so the orbits are more circular and they have more time for the scalar charge to, what's happening? For the scalar charge to grow up until it saturates in certain value. And then we are studying, what we are working on now is on generating the corresponding waveforms and trying to catch the signatures of the phi-mode excitation in the waveform. If it is a sufficiently strong effect that can be, distinguished from a GR waveform, then that would be great. So we could really probe the theory using gravitational waves. I think that's it. My summary, I'm out of time, but I can just read this. Phi modes are quasi-normal modes due to the presence of a scalar field. They have no analog in general relativity. They are not degenerated with the equation of state uncertainty. They are more suitable than GR modes for current generation gravitational wave detectors. And they could be used in principle to constrain massless scalar tensor theories of gravity. In particular, we're trying to do so using binary neutron star system and trying to look for signatures on gravitational waveforms. That is work in progress. And the to-do list is huge, but I'm just writing here a couple of items. We want to look at rotating neutron stars. So far, we just looked at static configuration, and we looked at radial modes. We want to look at non-radial ones, which are way more nasty. And then explore other theories, because in principle as well, this is not a particularity of scalar tensor theories, but whenever you have an extra degree of freedom, vector, tensorial, whatever, you would expect the emergence of different quasi-normal modes as I showed here. And that's it. Oh, and I have an announcement before you go home. I'm new here at ICN, and I have tons of thesis projects available if you guys are interested, just for the students. I didn't want to let go of the opportunity. Yeah, thank you.
Thank you. We have -7 minutes for questions, which means one short question. Marcelo.
Yes.
Do you use this effective theory to compute, for instance, the evolution of monopolar and polar gravitational waves because of the scalar theory? For instance, the parameters of the binary pulsar, can you constrain the nominal coupling with the emission of these monopolar and polar? It should be very small, otherwise it would perturb the usual plot that we saw in Taylor.
Right, but this effective field theory works for binary systems in particular. It is designed by that. I don't know of any sort of approach to do the same for isolated systems. But oh, right. Oh, you're talking about the Taylor. Yeah, sorry. Yeah, that sounds like a natural thing to do, and I'm not aware, but I would bet that somebody has looked at this. Yeah, I don't know. It's interesting.
Okay. Thank you again for this nice
Thank you.
talk. Thank you. We are at the end of our workshop. Let me, on behalf of the organizing committee, thank all the speakers, especially our lecturers, Professor Salucci, Professor Henry, thank you very much for being here. Professor Salucci is going to stay with us with a couple of days if you have any questions to him. So, what else? Thank you for being here for such a long time, so late. And so, you might know that in any organizing committee, there are two groups. There's the first group, who is the group who really does the work. And there's the second group who does nothing. I belong to the second group, okay? So, therefore, I would like to thank the real organizers of this workshop, Celia and Elias. They are the real heroes of this workshop. Thank you very much on behalf of all of us. Thank you.
May I say something? Okay. So, okay, I really thank both the one which are working, the one we are not working, because really it has been very, very good, and I liked a lot of workshop, new with even innovative aspect, and I really like to see very young people and stay until 7:30, to like listen science and physics. So really, I think that you have worked a lot. You have done very, very well. I think for me, a splendid workshop. And I will immediately, I will say that I will take one of those because she will be in SOC in next year. We will organize a meeting in Trieste, because Trieste will be the European Capital of Science in 2020. So CIS has given to me the honor, but also the problem to organize a conference. And now I am collecting the best SOC in the world, and I thought that Celia could really be careful. I see that not only is good scientifically, but organizing is very good. So thank you again to all. I don't know if Martin wants to add something.
Spanish.
Tengo sueño. No, nothing really to add except it's been really enjoyable. For many reasons, the science has been fascinating. For me, it's been a journey down memory lane because I spent so many weeks and months in Mexico between 1995 and 1997. Of course, the world has changed so much, as I said yesterday, but the hospitality of people here is just as strong as it was. I've enjoyed the food, but I've also really enjoyed so not just the gastronomia, but also the astronomia. Lots of really fascinating talks, and I've been really pleased at all the ways in which what I was asked to talk about, gravitational waves, has connections with the research that you're all doing here. So I really do look forward to visiting again, and I thank you for the invitation.
I just want to also thank all of you. I mean, for the students, this is the first time this workshop was translated, was first in Tuxtla, as I say. The connection with Mesoamerican was principal, the direction of this event, but now here in Mexico City, which we have more interaction with more students. Now we are here in UNAM. But also thank all of you. I hope that you enjoy the interaction with the researchers and in other parts of the country and also of the world. We hope that for next year we have the 4th edition for the workshop. So we are going to try to organize something for the near future. So thank you very much to you all.
Thank you. Game is over. No, thank you all of you, the lecturers, our speakers, everybody here, UNAM, there in the University of Chiapas, and we hope to make next year the next edition of this workshop. We don't know where, but hopefully we will meet again next year. So thank you very much. See you.
Game over.
The song is over.